Our goal in week 2 has been to introduce some of the key players that are essential to understand the overall energetic processes in the Earth. And one of the links that we haven't made yet is the one that relates to water and energy. We talked already a little bit about the greenhouse gas effect and how that is an energy recycler for the Earth as a whole. And water plays an enormous role both itself as a greenhouse gas and for the way it modifies a variety of other exchanges. Water also plays an enormous role in the triggering of stability or unstable conditions, and we'll want to set the stage for that understanding as well. First thing to remind ourselves of is that water is a hugely important energy carrier. Water in its liquid state even has important role with respect to the movement of kinetic energy. That is, the motion of water can contain a lot of energy, and so we have erosion and erosive processes that take place over the Earth. There is a slight change in the temperature of water associated with movement and dissipation, and that is associated with the fact that water has a very high specific heat. It takes a lot of energy to change the temperature of water, or a lot of energy is released when we reduce the temperature of water. And there is a large amount of energy involved in the movement of water through different elevation changes as well. But even more profoundly important than all of these things is the fact that phase changes involve huge energy transfers. The typical amount to evaporate 1 kilogram, or about 1 liter of water at room temperature, is that this takes 2.5 million joules of energy, or 2.5 megajoules, which is a lot of energy. In fact, to evaporate 1 millimeter depth over a 1 square meter area would take that 2.5 megajoules. So to evaporate 1 centimeter of depth would take 25 megajoules of energy over a 1 square meter area. 1 square meter is a small area for the Earth's surface, but even that is generating the energy equivalent that's not far off a liter of gasoline. And a liter of gasoline can be explosive, and so in fact can this phase change component. The key thing is to recognize that that energy is released when water condenses, and it is of course absorbed when water evaporates. And now the connection, of course, is that the evaporation usually takes place from the surface of the Earth, from lakes and from moist surfaces and from the ocean, and condensation usually takes place in the atmosphere. And this creates an extraordinarily important transfer of energy from land to the air. And it warms the atmosphere, it cools the surface of the Earth, it brings about a huge global transport system that plays an enormous role in the way the Earth works as a whole. And we'll see that that transfer process plays a huge role in triggering various atmospheric instabilities, which are manifested to our observations as things like tornadoes and hurricanes and thunderstorms. What we need is an efficient way of accounting for some of these water and energy exchanges and this process of evaporation. And one of the great ways that we've invented for doing that is called the psychrometric chart. If you get involved in some point in heating and ventilation systems and looking at condensation systems, this chart plays a huge role. A variety of other charts have been evolved and developed for meteorological purposes, but we thought we'd introduce this one for you because it makes the other ones quite easy to understand. Essentially, the psychrometric chart is a way of determining the moisture content of air at a given temperature and a given relative humidity. It also determines a thing called the dew point temperature, which is the condensation temperature associated with air. We'll explain that more in a minute. It also deals with a technical term called the enthalpy, but we really can think of that as another version of energy typically that takes place at constant pressure, which is more or less the way the Earth functions as a whole, with atmospheric pressures relatively fixed at a given altitude and a given location. We also have a very important measurement device called the wet bulb temperature, which is really a thermometer that's kept wet. And we also can determine the specific volume of the air, which is reciprocal of density. And the next link we want to make next week will be the connections that density plays in stability considerations and this key concept of buoyancy leading to the concept of convection. A few quick definitions here. Dry bulb temperature is the temperature at which air is measured with a thermometer. It's sometimes called dry bulb to distinguish it from this wet bulb temperature. Moisture content of the air we can measure in a variety of ways, but one of the ways that is very common is to measure this number of kilograms of the mass of water vapor that's contained in a certain mass of dry air, and that ratio is this moisture content that we're going to use as the key measurement. We'll see the numbers are not very high, but they play that critical role. And the other idea is the idea that air contains the maximum amount of water at a given temperature, and that's going to be represented by what's called the saturation line, which is often thought of as being the air with 100% relative humidity, or containing the largest amount of moisture that is possible under equilibrium conditions. I emphasize the equilibrium conditions because it turns out that in order to get water to change phase, to go from liquid to vapor or vapor to liquid, we need condensation nuclei. It's not easy to do that phase change, and if we don't have those condensation points present in the air, air will in fact allow us to get to relative humidities considerably higher than 100%, but in normal air over the surface of the Earth, that's extremely unlikely. Here's the basic idea. We have a temperature measurement that's increasing from left to right, and a moisture content that's increasing from bottom to top. And we have a line on here that represents the line of saturation. The saturation line represents this equilibrium where we can have a given temperature in contact with air, and it will achieve a certain equilibrium content of moisture. And that is represented by the saturation line. Sometimes there is a vapor pressure measurement for this as well. Points above the line and to the left of the line are considered to be liquid water, and the points to the right and below the line we're going to consider as being air that's in an unsaturated state. So this is air that might have moisture, but it's not as much moisture as it potentially could contain. The two other definitions that we can introduce at this point is the idea of relative humidity and the idea of dew-point temperature. Relative humidity is simply the amount of moisture compared to what the air could potentially hold if it were saturated, or the ratio of the moisture content at the current level of moisture to what it would have at saturation. So it's a kind of a vertical demarcation of the saturation curve, as we'll see in a minute. The dew point temperature is the temperature that we would get when we reach the saturation line as we move to the left. We can think of these 2 points as a kind of vertical distance in the relative humidity or horizontal distance from the saturation vapor pressure line in both cases. So it gives us, in a sense, our separation either vertically or horizontally from that line. So let's just show the basic idea here. A 70% relative humidity line is one that at every vertical location, every horizontal location, the vertical distance is 0.7 of the full distance of the saturation line. So the relative humidity of 70%, here's a 50% line, and the idea here is that the distance from here to here is the same as the distance from here to here. That represents 50% relative humidity. We get a bit of an optical illusion in this because the lines are expanding so rapidly to the right. The separation is growing, and this separation doesn't always look proportional, but if you look at it carefully, we've tried to draw this quite clearly so that this vertical distance is the same. This distance is 70%. And this allows us to write as many curves on this plot as we wish. In this case, we've shown 20%, 30%, 50%, and 70% relative humidity lines. One of the things that we have then is a grid location, so that if we want to choose a particular temperature, in this case 27 degrees and a relative humidity in about 40%, we can from that determine what the moisture content of the air. And we can do that by simply reading across to the right and getting that value. And this is typical values that we see in the atmosphere, where we have roughly 1% or perhaps 2% of the mass of a given volume of air is taken up with moisture, and the rest of it is dry air. And so that extra component of moisture in the air doesn't change the air properties dramatically, although it makes the air slightly lighter, but it does have a huge role because of that evaporative component representing these changes. If temperature and relative humidity are known, we can also determine this other component which we've just mentioned, which is the dew point temperature. To get to the dew point temperature, we simply determine where we are, and now if we read horizontally across until we intersect the saturation line, that temperature will indicate the dew point temperature. And so the dew point temperature can be read directly from this chart as well. The dew point temperature has enormous significance for us as humans and also for the planet as a whole. When air mass is on the surface of the earth, it can be quite warm and typically unsaturated, but if that air mass is forced to rise, it will cool as a result of the expansion process. And the point at which the dew point temperature is reached is basically the cloud base. It's the elevation at which the clouds will begin to be visible and form in the sky. So that's a fairly critical idea. The second part of this, of course, is that we can experience this dew point temperature all the time. When the surface of a windshield is cooled overnight, the air in contact with that sometimes reaches the dew point temperature and we get a condensation, so we get a wet windshield. Or in a warm shower, we sometimes have a warm temperature. The mirror is colder than that and the water vapor will condense as the air is in contact with the mirror, and we get that dew point temperature as well. A critical implication of this, though, is that we can measure in any particular temperature and any particular water content the energy content of the air as well, in kilojoules per kilogram of dry air. These lines represent an ability to read off points of equal energy, and so we can realize that as we shift locations, some shifts are possible by simply changing moisture content, but we don't actually need an energy input. If we move along the lines, we have constant energy. If we move between the lines, energy is required, either released or stored, depending on the direction of our transfer. The next lines that we can also add to the same plot, because of the predictability and the regularity of air and water, are the specific volume lines. Specific volume is just the reciprocal of density. It's now the number of cubic meters of air per kilogram of dry air, and so these lines can be shown on here. Water, air at typical temperatures often has a density of about 1.2 kilograms per cubic meter, which is this value close to here of about 0.8 for the specific volume of cubic meters per kilogram. So enthalpy is this measure of this total thermal energy. The wet bulb temperature is a new idea now. The wet bulb temperature is the temperature that you would get if you had a thermometer measurement location which is kept moist so evaporation can take place. And what we have is really a conversion of the sensible heat, that is the heat that's associated with temperature, into evaporative processes. And that gives us a very good measure of where we are. The specific volume we've already mentioned is that space occupied by unit weight or mass of air. These wet bulb temperature lines have basically an analogous role with respect to the enthalpy lines. They really represent that constant energy conversion process, and so these wet bulb lines will run parallel to our enthalpy lines. If the temperature and relative humidity are known, we can determine the enthalpy, the amount of energy in the air, and we can move to various other combinations as well. If the temperature and relative humidity are known, we can determine the wet bulb temperature as well by reading up, and we can get, again, parallel to these enthalpy lines, and we can read what the wet bulb temperature is by the same process that we read the dew point temperature. If temperature and relative humidity are known again, we can also determine that specific volume. So all of those things are available to us, which gives us an enormous capacity to navigate in complex situations. We'll be following up on these ideas in later lectures when we look at atmospheric stability and Earth circulation, precipitation, energy transfers, global circulation, even atmospheric circulation are all connected to these moisture changes, which play such a key role. Again, if you're interested, more information is available from other sources.